Exactly. Okay, so we are coming exactly to that. So the question is, what happens when you integrate over a pulse where the Bessel's function goes to 0, right? So this is my Rm, and in general this could be some point over here which is R prime. Okay, so there are two cases possible. So I can say that Rm belongs to the does not belong to the nth pulse, and Rm belongs to the nth pulse. If you want it very simply, you can say m equal not equal to n and m equal to n. These are the two cases that we have to worry about. So the first case, what do you think? It's a finite integrand being integrated. Should there be any problem? No, right? So we can even do quadrature rules or whatever. Second term is where there is a potential singularity. Potential, right? That's the keyword over here. Intuitively, do you think this will be a problem? What is, am I integrating g or grad g? Right, this integrand over here, am I integrating g or grad g? G, right? And g is of the form, for very small x, it is of what form? 1 by x or log x? So it's of the form log x for x very small. So it is an integrable singularity, right? So in this case, I don't have to worry about some kind of a principal value integral and all of those complicated things which I had in the surface integral case. Remember, in the surface integral case, the problem came from grad g, not g. Okay. So intuitively we know that this is not going to be very difficult. Okay. So that's one more advantage of volume integral equations, is that you are avoiding that the real singularity is being avoided. So you have an integrable singularity over here. Now we can go ahead and do this integration, and you can either use quadrature rules, but in this case sort of nature has been even kinder to us. The integral of, so what am I integrating? I am integrating this Green's function g r m r prime dr prime. Essentially this is the integral, right, over the nth pulse. This is the integration that I have to worry about. Now this, the way I have drawn these are square boxes of, let's say, size b. Now it turns out, I am just giving you information, that the integral of this Hankel function over a square box, there is no closed analytical form for it. Not surprising, because it's a Bessel's function. However, if I do the same integral over a circle, it turns out that there is a closed analytical expression itself for the integral. Okay. But we discretized it into squares, and we know the answer for a circle. So the approximation made is approximate your circle, sorry, your square by a circle of the same area, so that you get a closed form expression, so that you don't have the error of quadrature. When I do quadrature integration, there will be some error. I get rid of that error and I replace it by a new error, which is approximating a square by a circle. That error will go away as I make my discretization very, very fine. So that is the trick. You don't have to do it, but it's good to have closed form expressions. So the area should be the same. So b squared should be pi a squared. Okay. So that is what I will do. And once I know this, it turns out, I will just write down the final expression. You can do this integration yourselves looking at the handbooks. So 0 to 2 pi, I am integrating over a circle, 0 to a, h naught 2 k rho d rho d theta. This is integration over a circle, right? Rho d rho, I am missing a rho. Okay, there is a rho. Rho d rho d theta. That is the 2D differential element integrating, and I have my k h02. Okay, so I will write down the two expressions. So the first expression is for m not equal to n. So this is 2 pi a by k j1 of ka. So you notice the radius of this cylinder is appearing Okay, this is one expression. The second expression is where the singularity the alleged singularity appears, and the expression is again there is a closed form expression pi k a h12 of k a minus 2j. Okay, this is just information. We can actually go and show this integration. It's not very difficult. Okay, so this turned out to be so much more simpler than the surface integral equations because no singularities to worry about really. Rho mn is the distance. Yeah, so rho mn is Rm minus Rn, the distance between the centers of the squares or circles, that is rho mn, right. So what are we doing? We take one guy fixed, integrate over all of these pulses, right. So I get one equation repeated for all 9 testing points. I get 9 equations, 9 variables. Okay.